Okay, 9 a.m. and we can start. Okay, guys, so yeah, the last week of the semester. I asked you to either watch a video which I recorded a year ago, or read my notes, all right, to prepare for this recitation class, right? In order to save time, I started doing this like a year ago. Okay, so where in that video or those notes, I introduced, not derived, I introduced a traveling wave equation, right? So what are we going to do today? We will just review major points of that video, right? Okay, so first of all, we need it in order to move slightly further in optics, right? Because now we are moving into the world of optics, right? And so first of all, probably I should say, so what is a wave? In simple words, a wave is a disturbance which propagates. If you take a chord, okay, disturbance in a media which propagates. In this case, chord is the media. If you create disturbance, then it will, and release it, of course, then it will propagate in both directions, that direction and that direction. So in this case, we created a wave which is a transverse wave, right? Okay, so then, and there are two types of waves, longitudinal and transverse, right? I described the difference between them. So now, here's the equation which describes any of those waves. You can use the same equation to describe either longitudinal wave or transverse wave. It works for both, right? Okay, and now let's just start describing each of these parameters one by one. Let's start from the right. And so we have some function y, which depends on two variables, x and t, right? X, okay, it's a position, basically, right? Coordinate, and t is time, right? X in this case basically tells us along which axis wave propagates. In this case, a wave propagates along x-axis. So in this case, if this is the chord string, right, and wave propagates that way, so this is our x direction. If I align x-axis along that direction, so this wave will be described by this equation, right? So x, in this case, it's an axis along which wave propagates. Then what about y? Y, it's a displacement of a particle of a medium from a displacement of a particle from an equilibrium. So again, if we look at the chord, so right now all the particles of this medium is in equilibrium, right? And then if I disturb it, right, so you see, look at this knot, right? So if I disturb it, right, so now knot is displaced from the equilibrium, and this distance from the equilibrium, let's say 1 centimeters or 2 centimeters, right? That's what y is. So y, it's this axis, right? In this particular case, for this transverse wave, right? Again, x, it's a direction along wave propagates, and y, it's a displacement of the particle from an equilibrium position, right? So down, up, right? So displacement from an equilibrium. So that's what y is, right? So this is a place where plenty of students make mistakes, right? Okay. Then, okay, so pretty much now I can start filling up this table. So first, x, it's a, and now I'm going to introduce plenty of different quantities, different parameters, and every time I will be adding spatial quantity or spatial parameter or temporal, spatial or temporal, all right? Basically, since wave lives in both space and in time, in x and time. So of course, there are two types of different quantities describing life over wave, either in space or some parameters describing life of this wave in time. So that's why every time I'm going to add this word spatial, temporal, spatial, temporal. So first, with the variables, x obviously describes what happens with the wave in space. So that is the spatial variable, right? So let me write it down. So x And of course, the meaning, it's a spatial variable, right? Spatial variable x. And then t, of course, it's a temporal variable. T, temporal variable, right? Okay. Now, then, so we discussed this. Now, amplitude. Amplitude, okay, everyone knows that it's a maximum displacement of a particle. Again, this is not maximum displacement of a particle from the equilibrium. So that's the amplitude. Let's say 3 centimeters. 3 centimeters, right? Maximum displacement, amplitude. Then there is a periodic function, sine, right? Sometimes you can see cosine function, but it shouldn't. You shouldn't panic when you see, for example, cosine function instead of sine function, because what's the difference between sine function and cosine? If you grab some sine function and shift it by pi over 2, you will get cosine function, right? Pretty much, they both sine or cosine can be used to describe these traveling waves. This book uses sine function, so I also in this introduction use sine function. But anyway, so it's a periodic function, and inside of this periodic function there is x and time, spatial variable and temporal variable. So it means that if sine depends on x and time, it means that our wave is periodic in space, periodic in x, and also periodic in time, right? So it means that we should be able to introduce, not should be able, we need to introduce quantities describing periodicity of the wave, periodicity in space and periodicity in time, both. So now the second column, so now we need to introduce periodicity, right? So first, periodicity in space, spatial periodicity, right? Which parameter is used to describe spatial periodicity? It's basically, what is spatial periodicity? It's a distance over which a wave reproduces itself. Of course, everyone knows what I'm talking about, right? I hope. It's the wavelength. That's the meaning of wavelengths. Wavelengths, it's a distance along which a wave reproduces itself. Wavelengths, it's a spatial periodicity. Okay, so now we can add here, of course, we're going to use symbol lambda, right? Lambda, spatial periodicity. So spatial periodicity. Oh, you know what? Let me first write wavelengths, the name, and then I will write the meaning. Yeah, okay, sorry. All right, so let me write first name, wave, length, and then meaning, spatial periodicity. Wavelength, spatial periodicity. Okay, so that's the parameter which describes periodicity in space. Now, which quantity is used to describe periodicity in time? Right, again, because a wave is periodic in time, so there must be a parameter describing periodicity in time. And of course, everyone, okay, most of you are probably aware of, know where I'm going, right? Because what is a periodicity in time? It's basically a stretch of time over which wave reproduces itself. It's like here, spatial periodicity, it was a length over which reproduces itself. Now in time, it's a stretch of time over which wave reproduces itself. Right? Of course, I'm talking about period of the wave, right? We're going to use, of course, capital T, right? Name, period, right? So name of that quantity is a period. And physical meaning, temporal periodicity. Temporal, okay, maybe I can write temporal periodicity. Right. Okay, temporal periodicity. Now, next one. Since it's periodic in space and time, so of course we should be able to introduce frequency, right? Basically, um, how fast wave oscillates first in space, because it's periodic in space, and since it's also periodic in time, so of course we can introduce parameter describing how fast wave oscillates in time. So we need to introduce spatial frequency, and we also need to introduce temporal frequency. Let's start with spatial frequency. Spatial frequency is this parameter, this quantity, k. And the name of this quantity is wave number. Most of you never heard about a quantity like this, wave number. But if you ever going to work in, I know, optical lab or optical company, especially in the low frequency like infrared, far infrared, mid infrared, even lower microwave, right? This quantity is used a lot, right? Many spectrometers, if you use them, they by default plot you, for example, intensity of absorption or intensity of emission versus wave number by default. Of course, you can change it, but usually by default versus wave number. So I'm telling you that it's not just a bizarre quantity which was introduced just to torture you. No, it's a very, very useful quantity, right? So now k, this k, wave number, k. The name is, of course, as I said, it's a wave number, right? And physical name, it's a spatial frequency. You know what? Okay, let me first write the formula, definition, and then a wave number name. Okay. Since, okay, let me erase it. Right. So first, let me write sort of definition. By definition, it's a 2 pi over lambda, and only then I will write a name. So that's how wave number is introduced. 2 pi divided by spatial periodicity lambda. Okay, and now let me write the name and the meaning. Name wave number. Right. And meaning spatial frequency. Right. Basically, in this case, it's how many wavelengths you can fit into pi radians, right? Basically, how fast a wave oscillates in space, spatial frequency. Okay, now, and of course, units, radians over meters or centimeters. But very often, radians are just omitted because you know what is inside of radians? Nothing. Radians is just empty, right? The way we introduce radians, it's a length over length. Arc length of a circle versus the radius. That's how radians were introduced. So inside of radians, there is nothing, right? So usually units of wave number, it's a reciprocal of meters or reciprocal of centimeters, right? Okay, so now we need to introduce the temporal frequency in a very similar way, right? Because there is lots of symmetry between temporal world and spatial world. Okay, temporal frequency, we're going to use omega. It's this parameter in front of the temporal variable, right? Spatial frequency, you see in front of spatial variable, and now temporal frequency in front of temporal variable. So omega, angular frequency, name is angular frequency. We introduced it by definition, basically in a similar way. You see, 2 pi over spatial periodicity. Now we need to take the same 2 pi, but now we need to divide it by temporal periodicity, right? So definitions are very similar, right? So 2 pi divided by spatial frequency, and now it's a 2 pi divided by temporal frequency. So that's how angular frequency is introduced. Meaning of this angular frequency, it's basically temporal periodicity. How fast the wave oscillates in time. Right. So name angular frequency, and the meaning, it's a temporal periodicity. Temporal frequency, sorry. Temporal frequency, right? Okay, so now, again, another thing, look, so spatial frequency here, spatial variable there, pretty much all spatial information about the wave can be found in this term. All spatial information is here. Then omega, temporal frequency, t, temporal variable. Again, all temporal information is here, right? All temporal information about the wave is here. Then let me check what else I need to mention. Probably phi naught. Phi naught, our name is initial phase. Okay, let me write that down. So this is initial phase. It's a constant. Usually, if a wave is given, that initial phase is also given, right? And basically, it does what? It just shifts the whole wave, for example, like in this direction or that direction along x-axis. For example, like I told you about cosine function. Sometimes cosine function can be here. How can we get cosine function out of sine function? If this initial phase is pi over 2, if phi naught is pi over 2, then this function sine can be changed to cosine function. Of course, without initial phase. It will be cosine kx plus minus omega t. So that's what initial phase does. It just shifts the wave, the whole wave, along x-axis in a positive direction or negative direction, depending on the value of that initial phase. And then next, minus plus. Those signs give us direction of wave propagation. Of course, you remember, wave propagates along x-axis. But which direction, plus x or minus x? These plus minuses give us that information, right? So minus tells us if there is a minus. Okay, let me write over here. All right, so minus tells us that wave travels, which way I wrote in plus, travels, yeah, in plus x direction. So if you have a minus between this term and that term, it means that the wave propagates in the positive x direction. So you need to remember, you see this flip, minus give us positive x direction. And if you have plus, then of course, okay, these guys, it means that the wave travels in minus x direction. So we almost described everything about the wave, but what else is still missing? Very important parameter, very important quantity. Wave propagates. It means it travels. If anything travels, of course, it makes sense to ask the question, how fast that something travels? What about the speed? Speed of this wave, right? Okay, so now let's introduce speed. And okay, you see, every time when I talked about all these parameters, every time I added that this parameter is temporal or spatial or temporal, right? What about speed? Is it a temporal quantity or spatial quantity? Actually, it's neither of those. Because look, even from physics 1, you remember what did you need in physics 1 in order to find, for example, speed over a car or speed over a particle? In order to find the speed, right? Just a second, let me. Okay, this muted. So what did we need in order to find the speed of a particle? You need to know the distance, and you the distance, and you also needed to know the travel time. So you take distance divided by the travel time in order to find the speed. What is distance? It's a spatial quantity, right? Spatial parameter. And travel time, it's a temporal quantity. So you see, even back then in physics 1, you needed to use both quantities from temporal world and quantity from spatial world in order to find speed. Speed, it's sort of like a mix. You need to juggle both quantities from both worlds, temporal world and spatial world, right? The same here. In order to find speed of the wave, you need to take a quantity from the spatial world and quantity from the temporal world, right? So in order to find speed. Okay, again, in the video and in my notes, I derived it basically, right? So now I will just write the result. Speed of the wave, of course, right? So which way I wrote? Oh, just speed. Okay. V equals first quantity from the temporal world, omega, and divided by the quantity from the spatial world, omega divided by k. So that's how wave can be found. If you're not sure, if you forgot about the formula, you can just easily look at the units. Units of omega, 1 over seconds. Units of k, 1 over meters. As a result, meters goes upstairs, seconds in the denominator. You'll get meters per second, right? Okay, so that's our first way of finding speed of the wave. And again, you see, we mixing parameters from the spatial world and temporal world, because as I told you, speed, it's neither of those, right? Sort of speed works as a bridge between this temporal world and spatial world all the time. I will say this. I will say this word a few times when we start looking at the problems. But there is another way of finding speed. Look, we know definition of omega. We know definition of k. So if you write that down, so it will be 2 pi over t, and divided by 2 pi over lambda, right? Just use definition. So lambda goes in the numerator, t in the denominator. You will get lambda over t. So that's another way of finding speed, right? So you can write it v as lambda over t, or since period and frequency, they're reciprocal of each other, right? So we can also write it as lambda times frequency. So that's the second way of finding speed of the wave, right? Okay, this v equals lambda f is used in optics a lot in order to move, for example, from the wavelengths to the frequency of some light electromagnetic wave, right? Okay, so that's what I wanted to describe. And also, you know what? Maybe let me also write omega in terms of this frequency f. All right, f is just a frequency. All right, maybe I will also write so omega equals 2 pi divided by t, or again, since t is 1 over f, so we can write it as 2 pi f. Okay, just okay, that's it. That's what I wanted to review. Let me check if I actually mentioned everything. Or maybe another thing I should have mentioned, that this whole structure, kx plus minus omega t plus phi naught, all this structure is called the phase of a wave. Phase of the wave, right? Okay, that's it. And now let's start looking at the problems. Problems are reasonably easy. Usually students don't have significant troubles on the exam with the problems like that. Okay, so what do we have? Okay, it's a chapter 16. It's actually volume 1, that volume of the book which you used in physics 1. In problem 14. So there is a wave, right, which travels to the left with this speed 2 meters per second. So speed is given. So we have a wave, right? Travels to the left, it basically means the author assumes that we will realize that to the left means negative x-axis, negative x direction to the left. All right, and then there is information about the wave given in this plot. So you see, we have d. It's basically displacement of a particle of the medium. Basically, it's a y, right? Yeah, sometimes people can use different symbols. Instead of y, they use d, right? Why not? It's not a crime, right? But you just need to understand it's a displacement of a particle of a medium from an equilibrium, right? And that is in centimeters, right? And then we know what happens to the wave in time, right? Okay, and we need to realize what we have here. You see, wave depends on both x and time, right? So depends on space and time. And since it's difficult for our brains to imagine simultaneously what happens in space and time, it's complicated, right, picture. So we usually, to simplify our life, we usually freeze one of the quantities and observe what happens to the wave in terms of the other quantity, the other variable. For example, we can freeze x and observe what happens in time. And that's what we have here. At the end of the video, I discussed that. So look, we have information about time, and it happens x equals 0. It should be x equals 0. I don't know why I wrote t. All right, x equals 0. So pretty much, that's what happens with the wave if you sit at point x equals 0. Right, let's say wave propagates that way. This is your origin, and you sit there, right, and observe what happens to the wave. You see, so at t equals 0, first it's a halfway up, then it starts going down. Here it's a 0, then go. So pretty much you don't move in x. You just sit here and observe with the watch and observe what happens with the wave. It goes up and down, but you don't move in x. X equals 0. And you remember how do we call this type of graph? Again, at the end of the video and at the end of my notes, this is a history graph. X is fixed, and then you observe what happens with that particular point x equals 0 in time. It's a history of this particular point x equals 0. So this is called a history graph. Okay, let me write that down. So it's a history graph, right? And so what else? Pretty much, yeah, time is in second. Pretty much that's it. So now we should be able to answer a bunch of questions, and at the end I will add additional questions because I think that this problem is not exhausted, right, in terms of finding all possible parameters, right? Okay, so now first we need to find amplitude. Okay, I will probably write it here. Amplitude. Amplitude, you remember, it's a maximum displacement of a particle from an equilibrium as the wave propagates. By looking at the history graph or any other graphs, like a snapshot graph or history graph, amplitude you can read immediately. Maximum displacement of a particle from an equilibrium. So in this case, 6 centimeters. Usually students don't have any troubles understanding that. All right, so A equals to 6 centimeters directly from the graph. You can read that. So now part B, we need to find frequency B. We need to find, and careful guys, if the problem just asks about frequency, it means F. Because if somebody would be interested in angular frequency, they would actually write find the angular frequency. If the problem says find frequency, it's just F. So what about F? So first, again, let's realize F, which quantity is this, spatial or temporal? Obviously, it's temporal quantity. It basically describes how fast a wave oscillates in time. Frequency, it's a temporal quantity, right? So it means that we should be able to get that information from this graph, because in this graph, we have plenty of temporal information. But of course, spatial information is completely missing because x is frozen. X equals 0. So spatial information is missing, but temporal, plenty. So we shouldn't have any troubles finding temporal quantities. Frequency is a temporal quantity. You should be able to get it from the graph easily. So, since f equals, you remember, 1 over t, reciprocal of the period, right? Okay, so let's try to find the period. F equals 1 over t. So, can we find period? Period, it's again temporal quantity. And period, it's a stretch of time, you remember, over which wave reproduces itself. It's right in front of us. Stretch of time over which wave reproduces itself. So at this point, we have, okay, minus, okay, amplitude, right? So the wave at this point, and then wave over this stretch of time, wave reproduces itself. So this is period. So if you have a history graph, period is right in front of you. You just look, find look at the proper points and find and read, not find, read the period. So basically, this is the period. All right. Stretch of time or period of, yes, stretch of time over which wave reproduces itself, right? Or between, for example, this point and that point, it's the same, right? So period from the graph, t equals, so it's a 0.8 minus 0.2 seconds. 0.8 seconds minus 0.2 seconds equals to 0.6 seconds directly from the graph. So now we just need to take a reciprocal of that. F equals 1 over t, 1 over 0.6 seconds. So it will be, 10 goes upstairs, so it will be 10 over 6. So it will be, probably I will leave it 10 as 10.6, 10 over 6. Yeah, let's leave it like this. Seconds. Oh yeah, in reciprocal of seconds. Seconds to the power of minus 1. Right. Actually, in my notes, just now I realized that I forgot to put power of minus 1. I need to fix it. Okay, so that's the period. Unknown frequency. Next, okay, now part C. What about wavelength? With wavelength, it's slightly, I want to say more complicated, but not that much, right? Wavelength is what? It's a spatial parameter. It's a spatial periodicity. It's a spatial quantity. And as I already mentioned to you several times, in the problem, the way it is given the problem, right? Spatial information is basically missing. In the graph, we have plenty of temporal information. We know how wave behaves in time. But what do we know about the spatial, what in terms of spatial information? What do we know in terms of spatial information? Only that this graph was recorded at x equals 0. Pretty much spatial information is missing completely. So how can we find spatial quantities? It looks like it's almost dead end.
You can use this. You can use the speed to find the wavelength.
Yes, exactly. Speed, as I told you, it's a neither temporal nor spatial quantity. It works as a bridge. So we can use that bridge to move ourselves from this world of temporal quantities to the world of spatial quantities. And speed is given. So that's why I told you over here that speed works basically effectively as a bridge. Right? So that's speed in this case will save us. If this information were not given, okay, this problem wouldn't be solvable. Not enough information. We would not have enough information, right? Okay, let me write. V works as a bridge between temporal and spatial quantities and spatial parameters. Okay, maybe, yeah, let me put a period. Okay, so now Lambda, yeah, we can first find, for example, frequency we found. Frequency we found, so we can use this formula for the speed, right? V equals lambda f. Yeah, I think this will be the best. V equals lambda f, right? V is given, so we need to find lambda. So lambda equals to V over f, and f we found in part B. So V is 2 meters per second divided by frequency is 10 over 10 over 6. All right. Reciprocals of seconds. So seconds will be cancelled because this second will go upstairs, this second downstairs, so they can cancel. Meters will be left, and so this 6 goes upstairs again, giving us 12 over 10, so it will be 1.2 meters. Let me check. Yeah, 1.2. So it will be 12 over 10 meters, so it's a 1.2 meters. So speed allowed us to find that. So then what's next? Okay, so pretty much according to the book, the problem is over. We found everything that this problem asked, but I added additional questions because basically I want to write at the end the traveling wave, right? So let me add additional questions. Add additional questions. So now this will be part A, B, C, D. Part D. In part D, let's find wave number K. Wave number. Okay, quite often I abbreviate just W/number, wave number. I'm just lazy to write wave. All right. Okay, so wave number, again, it's a spatial quantity, spatial frequency, wave number, right? So, so how can we find? By definition, 2 pi over lambda. Lambda we just found in the previous part, right? So, as a result, I can write K equals 2 pi over lambda, right? Lambda is over there, 2 pi divided by 1.2 meters. So it's a pi over 0.6. Units reciprocals of meters. Pi divided by 0.6 meters over 1. Usually when people talk about wave number, they don't mention radians, but tacitly assume that radians, of course, there. It's strictly speaking, it's a radians per meters, but usually radians are not mentioned. I don't know why. But whenever people talk about angular frequency, most of the time they talk about radians per second, right? It's not a big deal. Okay, so K is here. Now I guess we need to find omega because I want to write this equation, right? So omega, yeah, A, B, C, D, E. Now what about angular frequency, omega? It's not W, it's omega, small Greek letter omega. So again, by definition, 2 pi over T. And T we found over here in part B. So omega equals to 2 pi over T, right? So T is 0.6. 2 pi over 0.6 seconds. So it will be pi over 0.3. Yeah, okay, that's correct. Pi over 0.3. All right. Radians per second. Okay, at this point, we're almost ready to write the equation, right? And actually, let me write that down. Based on what we found. So now it will be D, not Y. It will be D. So now D, which will be a function of x and time because wave propagates in the x direction, we assume. Actually, not assume, it's given. X equals 0, so it means in the x direction. So amplitude, of course, we can see it's 6 centimeters, right? Of course, you can convert to meters, but it's not a big deal. Just your displacements will be in centimeters, right? So it's fine. Then sine k. We found pi over 0.6, right, times x, right? Pi divided by 0.6 times x. Then plus or minus should we use?
Plus.
We know, yeah, we know wave propagates to the left, which is negative x direction. Maybe I should emphasize, right? So means minus x direction, right? So it means that, of course, we must use plus, right? Plus travels in the minus x direction, plus. Omega pi over 0.3, pi over 0.3, and times t, and plus phi naught. Phi naught is still not known. We need to find phi naught. That's why I wrote this sort of not in the final form, not at a complete form, because in order to have complete form, we need to find phi naught. How can we find phi naught? Based on what is given on the plot. Look, we know that all this graph, it happens at x equals 0. So x equals 0. Then as a result, we have two unknowns, t and phi naught. But t, what if we take any point on this graph? For example, let's say probably the easiest point, t equals 0. And displacement can be seen on the plot. If t equals 0, so displacement you see 3 centimeters. So if we take this particular point, right, and apply over here, we should be able to find this constant. This constant is a constant of the wave. It doesn't matter which point in time you use, that will be the same constant. So we just need to take one particular moment of time and apply it for this graph. And we know that all this graph happens at x equals 0, right? So that's the way of finding initial phase, right? So from the figure, let me write that down. From the plot. From the plot. All right, so we know x equals 0 and that plot, right? And let's pick t equals 0. And pick t equals 0. And we know that the displacement at t equals 0 equals to 3 centimeters. So we can use that fact. Right. Again, if you don't like t equals 0, not a big deal. You can pick this point. You will have to mess with more terms over there. But of course, at the end, you will end up with the same answer. But in this case, t equals 0 is probably the easiest point to use. All right, so now, so let's plug it over here. All right, let's plug it in so it will be 3 centimeters. It's a left-hand side here, then amplitude 6 centimeters, and then sine, then pi over 0.6 times 0, so it's a 0, then plus pi over 0.3 times t, also 0. Okay, it's not visible. Okay, and then plus phi naught. All right, so it's equals to 6 sine of phi naught. 3 equals 6 sine phi naught. Of course, you can take arc sine. All right, so sine of phi naught equals to 3 over 6, 1 over 2. Okay, I know that by heart. Phi equals pi over 6. Okay, phi naught, not phi. Phi naught. Okay, am I right? Yeah. Pi over 6. Okay, so that's basically, after this, we can write the final form of the equation. I'm almost out of space, but of course you can easily plug it over here instead of phi naught, right? In order to get the final form of the equation, right? In your homework, there will be also a problem where you will have to find phi naught, which is not going to be 0. Okay, so once you practice a couple of times, it's quite straightforward. Usually on the exam, most of students do well. Right? And most of this stuff can be applied for electromagnetic waves. Right? But for the electromagnetic waves, what can you say? Usually problems about electromagnetic waves doesn't tell you the frequency, or doesn't tell you the speed of the wave. They just tell there is an electromagnetic wave propagating, blah, 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 in this direction with this, that, right? Whenever you see electromagnetic wave, it should trigger your brain immediately. The speed of the wave is the speed of light. 3 times 10 to the power of 6. Oh, wait, times to the power of 8, right? So will be 3 times 10 to the power of 8. Now, another problem, but I will just probably be able to plot and discuss it quickly, but we wouldn't be able to finish it. So let me separate it like this. It's not from the book. It's just a problem. Let me put a bullet. And again, there is a wave and this plot is given. So let's say we have y is in centimeters. Right. So here we had displacement d. Now displacement from the equilibrium y. Right. And this plot is given versus x. X is, why I'm writing brackets like c, centimeters. Right. And the plot, this is the plot. All right, so let's see. Something like this, sine function almost. Right. Then this point is 5. This point is minus 5. Right. Then this point is 10. Then 20. And then 30. So wave is given. So we have a wave. Right. And we also know that this wave propagates with the speed v equals to 10 centimeters per second. But now I can actually show the direction of the wave on the graph, because now we have spatial information is given. So I can show it like this. So v, right, equals 10 centimeters per second. Over here I couldn't show because we have a temporal information, right? I cannot show that no wave propagates in the negative, in the negative time direction, right? So nothing propagates back in space, back in time, right? So there, of course, I had to write traveling left, but here I can show with an arrow, right? Okay, so and that's what is given, and this graph was recorded at t equals 0. This graph was recorded at t equals 0. As a result, how do we call a plot like this? This was a history graph. Position was fixed. Now time is fixed. How do we call graphs like this? It's basically a snapshot graph. That's what you can get with the camera, right? If you, for example, wave on a cord, well, you can take a picture of that snapshot graph. So this is a snapshot graph. Snapshot graph. So now we have, you see, opposite situation to the previous problem. There we had plenty of temporal information and spatial information was missing. Here we have plenty of spatial information And as a result, this graph is called snapshot graph. But temporal information is missing except for t equals 0. We know that this was recorded at this moment of time. But now you remember what can be used to move from the spatial world to the world of temporal quantities. Speed, and the speed is given like there, right? So that's the that's the major difference between that problem and this problem, right? Otherwise, the rest will be similar to that, right? How to find. And another thing, over here, whenever you see this history graph, the distance between, for example, these two troughs gives us what? Period, because it's a stretch of time over which wave repeats itself, reproduces itself. It's basically, over here we have temporal periodicity. But when you have a graph like this, now we know what happens to the wave in space, right? And what can you say about this distance between these two crests? It's a distance now over which wave reproduces itself. It's a wavelength, spatial periodicity. This is the wavelength. All right. If you see a snapshot graph, you can get the wavelengths immediately. If you have a history graph, you can get period immediately, right? So let me show this over here. So this will be wavelength. All right. The rest is very similar. And again, and I told you what's the major difference. Here we have plenty of temporal information. Now here we have spatial information. But you remember, speed can move you from the world of temporal quantities to the world of spatial quantities. And the opposite direction also it works, right? Okay, we'll see. Maybe I will just send you my solution to this problem because it's very similar, right? Tons of questions, A, B, C, D, E, but again, each of them, answering each of them, it's just like 5 to 10 seconds, right? Or maybe next class we will discuss that. I will think about it. Okay, guys, thank you. All right, if you have questions, ask. If not, I will see you tomorrow in the lecture.